I'll now give a very brief overview of the method of partial fractions. So this is applied to integral of rational functions, where rational functions mean that's the ratio of two polynomials, p and q. Before starting to apply the partial fractions technique, you should look for some special forms, which are some examples I'm reporting here. So see here, if the top is the derivative of the bottom, then you could do a substitution, u equals the denominator, and you would get it down to a logarithm. Here I give you an example. So 2x plus 1 divided by x squared plus x plus 2. You recognize that if you take u to be the denominator, then the derivative of u is exactly what you have there, and you're going to get a logarithm. Another form is you have this derivative divided by 1 plus this polynomial squared, which arises from arctangent. And I'm giving you an example here, x over 1 plus x to the fourth. You can realize x to the fourth is x squared squared, and then x is more or less the derivative, so the substitution u equals x squared will be effective in this case, and you will get it to an arctangent. So once you rule out these possibilities, then you can start applying the partial fractions method. So what does this method say? It says that, well, first of all, if the degree of the numerator is greater or equal than the degree of the denominator, then first you need to manipulate it or divide. You can use long division, for example, to bring it down to the case where the degree of the numerator is smaller. Now, if you're in that case, or if you are reduced to that case after doing the division or your algebraic manipulations, then you can factor the denominator, and according to how the denominator factors, you will try to decompose your fraction into different types of simpler fractions. There's basically three cases. You can either have distinct linear factors. So an example here, suppose your fraction was 3, that's your p of x, and the denominator factors as x plus 1 times 2x minus 3. Then those are linear in the sense that they are degree 1 and they are different from each other. Then you look for the composition of the form a over x plus 1 plus b over 2x minus 3. So you just put one constant term on top of each factor. In the case where you have repeated linear factors, such as here, so the numerator p of x would be x plus 1, and the denominator is 2x minus 3 squared. So that means there's two factors that are both equal to 2x minus 3. Now in this case, you keep adding fractions whose denominator is going to be 2x minus 3, but with increasing powers. So here we have a over 2x minus 3 with a power of 1, and then plus b over 2x minus 3 with a power of 2. If this was cubed, then I would add another one, c divided by 2x minus 3 cubed, and so on. The last case is if we have a quadratic irreducible, which means it's a polynomial of degree 2 that cannot be factored into polynomials of degree 1. And I'm giving you an example here. Suppose we have x minus 1 over x times x squared plus 3. Well, x is a linear factor, so it gets an a on top of it, a over x. But x squared plus 3 cannot be factored anymore in real numbers. So that's a quadratic irreducible. And on top of a quadratic irreducible, you put a linear term, so of the form bx plus c. And that's covering the main cases. Now, why is this technique useful? It's because then it brings these complicated fractions into simpler ones, that the ones that I'm here calling basic blocks. What are the basic blocks? There's these three types of different denominators that you can get there. So one is simply a over x, or more in general, a linear term that would just be a logarithm. The second block would be a divided by a power, x squared, but more in general, just a power of a linear term, and that integrates as a power, so here 2x minus 1, but if this was cubed, then it would be to negative 2, and so on. And then the last block, that's the one on top of a quadratic irreducible, it's of the form ax plus b, which you can separate into this term, which is going to be, with a substitution, come out to be a logarithm if you substitute u equals 1 plus x squared. And the term with a constant will just be coming from an arctangent. And then here, so these are the most basic ones, and then here I'm just replacing this just x with a linear term. So the first block would be something like this, logarithm. The second block would be something like this, so a power, and the third one something like this, so a combination of logarithm and arctangent.